And now in this lecture we'll answer two questions. In the first question, we find out the area of this green shape, and in the second question, we find out the length of line segment AP is equals to x using two different methods. So we start with the first question. In the drawing, we have a semicircle. Note that BC equals to 10 units in its length. That is to say, the diameter of this semicircle is 10 units. PC equals to 8 units in its length. This is angle ABC. This is a right angle. And our task is to find out the area of this green shape. So first of all, we join points B and P together by a straight line. By joining points B and P, we created the peripheral angle BPC. This is peripheral angle BPC that subtends on BC, that is the diameter of the semicircle, and according to rule 5, any peripheral angle that subtends on the diameter of the circle or a semicircle is equal to 90 degrees. So I repeat rule 5. According to rule 5, any peripheral angle that subtends on the diameter of the circle or a semicircle must be equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle. This is peripheral angle AEB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle AEB is equal to 90 degrees in its size. So I already mentioned before, we can implement rule 5 in our drawing because we have in our drawing peripheral angle BPC that subtends on BC, that is the diameter of this semicircle, and therefore according to rule 5, peripheral angle BPC is the size of the peripheral angle BPC is equal to 90 degrees. So, in the next step, we'll implement the Pythagoras theorem on this right angle, triangle BPC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, by PT is the ratio for Pythagoras theorem. In this right angle BPC, BC is the hypotenuse, so BC square is the square of the hypotenuse, and it is equal to BP square plus PC square. And again, according to the Pythagoras theorem, in the right angle BPC, BC square, that is the square of the hypotenuse, equals to BP square plus PC square. BC is 10, therefore BC square is 10 squared, that is 100, and it is equal to BP square. BP is the missing sign, so I'll leave it as it is. BP square plus PC square. PC is 8, therefore PC square is 8 square, that is 64. So in total, if you found out that 100 equals to BP square plus 64. Here we subtract 64 for this equation, and we get that BP square equals to 100 on 64 is 36. So BP square equals to 36. Here we take wrote out the equation and get that BP equals to the square root of 36, that is 6. So the missing side BP equals to 6 units in its length. Okay, this is the missing side BP, that is equal to 6 units in its length. It is given us the question that AC is a straight line. So if we focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angle here at the left side of AC at point P? We have this angle that is a right angle plus this missing angle. The total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we define angle BAP, this angle as alpha. So in the right angle BPA, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. It is given us the question that angle ABC is a right angle, it is equal to 90 degrees in its size. Angle ABP equals to 90 degrees minus alpha, therefore this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is equal to 90 degrees. This is the size of the big angle, angle ABC, according to what is given in the question. So this missing angle must be equal to alpha. In the right angle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, we prove that the right triangle ABP is similar to this right triangle BPC according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found out that all the figures of this right triangle ABP are correspondingly equal to all the figures of this right triangle BPC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So we actually found out that the right triangle BPC is similar. This is the sign of similar to the right triangle APB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle APB over side BC of the right triangle PBC is equal to side AP of the right triangle APB over side BP of the right triangle BPC. And also side PB, actually side PB is the common side that belongs to both triangles. So side PB of the right triangle APB is equal to side PB of the right triangle APB over side PC of the right triangle BPC. So repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side AP, the side AB of the right triangle APB over side BC of triangle BPC is equal to side AP of triangle APB over side PB of triangle BPC, and it is also equal to side PB of triangle APB over side PC of triangle BPC. AB is the missing side, so we leave it as it is. Over BC. BC is 10, according to what is given in the question. And it is equal to AP. AP is the missing side, so we leave it as it is. Over PB. We already found out that PB equals to 6. And it is equal to PB, it is 6 over PC. PC is 8. So in total, we have found out that AB over 10 equals to AP over 6 equals to 6/8. So those two expressions that are equal to each other, therefore we get equation 1 from those two expressions. According to equation 1, AP over 6 equals to 6/8. AP over 6 equals to 6/8. Here we multiply this equation by 6, and we get that AP equals to 6 times 6 is 36 over 8. So here we divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, and 8 over 4 is 2. So in total, we found out that AP equals to 9 halves. Again, AP equals to 9 halves. So this is side AP, this is equals to 9 halves. Those two expressions are also equal to each other, so we get equation 2 from those two expressions that are equal to each other. According to equation 2, AB over 10 equals to 6/8. AB over 10 equals to 6/8. So according to equation 2, AB over 10 equals to 6/8. Here we multiply this equation 2 by 10, and we get that AB equals to 10 times 6 is 68. Here we divide both the numerator and the denominator of this number by 4, and we get that 60 over 4 is 15, and 8 over 4 is 2. So in total, we have found out that AB equals to 15 halves. This is side AB, is equals to 15 halves units in its length. In the next step, we will define the center of this semicircle. This point is point O. The diameter of this semicircle is 10, therefore the radius must be equal to half of it, that is to say the radius must be equal to 5. So the radius OB is 5, and the radius OC is also 5. In the next step, we join points O and P together by a straight line. Point O is the center of the circle, point P is the point on the semicircle itself, therefore OP is the radius of this semicircle, that is 5. In the next step, we define angle POB, this angle is theta, and we will implement the law of cosines in this triangle, triangle POB. According to the law of cosines, the law of cosines is true in any triangle. According to the law of cosines, this is triangle ABC that could be any triangle. The length of side AB is A, side AC equals to B units in its length, side BC equals to C units in its length, angle BAC equals to theta degrees in its size. So in this triangle ABC that could be any triangle, the following equation is true, that cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. So we will implement the law of cosines in this triangle POB. According to the law of cosines, in triangle POB, the following equation is true. Cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. So repeat again, in triangle POB, according to the law of cosines, the following equation is true, that cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. 5 square is 25, plus 5 square is 25, 25 plus 25 is 50, minus 6 square, 6 square is 36, so it is minus 36, divided by 2 times 5 times 5, 2 times 5 times 5 is 50, so in total we have 50 minus 36 is 14 over 50, so in total we have found out that cosine theta equals to 14 over 50. We would like to find out the value of theta itself. In order to find out the value of theta itself, we'll operate the inverse function of cosine, that is our cosine, on the result 14 over 50. In this way we get angle theta itself. Exactly like the following equation. We know that the inverse function of a square is a root. Okay, so if we operate the inverse, the square on number 3, the square of 3 is 9. Now in order to get number 3, again, we have to operate the inverse function of a square that is a root on 9. And we know that the root of 9 is 3. So by implementing the inverse function of a square that is a root on the result, we got the original number 3. That is to say, the inverse function cancels out the action of the function. So in order to find out the value of theta itself, we have to operate on the result, that is 14/50, the inverse function of cosine, that is r cosine. So we will operate the inverse function of cosine, that is r cosine, on the result, that is 14/50, and the result must be angle theta itself. Okay, and the r cosine of 14/50 is equals to angle theta, and angle theta equals to 73.73 degrees in its size. Okay, angle theta equals to 73.70 degrees, 73.74 degrees in its size. So actually, this is angle theta. The size of angle theta equals to 73.74 degrees in its size. So our task is to find out the area of this green shape. In order to find out the area of the green shape, we have first of all to find out the area of this segment VP. So what is the area of segment VP? From the domain, it is very easy to see that the area of segment BP is equal to the area of sector OBP minus the area of triangle OPB. So repeat again, we have found out that the area of segment BP is equals to the area of sector BOP minus the area of triangle BOP. So what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. So repeat again. Again, a sector is a portion of a circle enclosed by two radii and the arc between them. Okay, this is sector BOP with two radii OB and OC of the semicircle and the arc BP between the two radii. And the area of a sector is equal to pi r square, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So, the area of the sector BOP is equal to pi r square times the angle between the legs of the sector, that is 73.74 degrees over 360 degrees. R is 5, therefore r square is 25. So pi r square is 25 pi times 73.74 degrees over 360 degrees. The value of this expression is 16.088 square units. So if you found out that the area of sector BOP is equal to 16.088 square units. So what is the area of this isosceles triangle? Triangle BOP is an isosceles triangle because side OB equals to side OP equals to 5. Side BP equals to 6. So we have the rule that the perpendicular to the base of an isosceles triangle bisect the base. The base of this isosceles triangle, BOP is BP. So from point O, we will go perpendicular to the base BP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and B, the base BP. This point is point M. According to the rule that I mentioned, the perpendicular OM to the base PB bisect base PB. PB is 6, therefore half of 6 is 3. So MP is 3. So in this right triangle OPM, 5 square minus 3 square is equals to OM square. 5 square is 25 minus 3 square, that is 9. 25 minus 9 is 16. So OM square equals to 16. Here we take out all of this equation and finally get that OM equals to the square root of 16, that is 4. OM equals to 4 units in its name. So the area of any triangle is the base of the triangle times the height of the base over 2. The base is PB, so write it down. So the base is PB times the height is MO because it squares 90 degrees with the base over 2. PB is 6, MO is 4 divided by 2. 4 over 2 is 2 and 2 times 6 is 12. So total, if you found out that the area of this isosceles triangle OPB is equal to 12 square units in its size. So the area of sector POB, that is 16.088, minus the area of this associated triangle POB, that is 12, is equals to 4.088 square units. So in total, we found out that the area of segment BP is equal to 4.088 square units in its size. Our task was to find out the area of this green shape. So what is the area of the green shape? The area of the green shape is equal to the area of the right triangle APB minus the area of segment BP. So repeat again, we should find out that the area of the green shape is equal to the area of the right triangle APB minus the area of segment VP. So what is the area of the right triangle APB? AP equals to 4.5, side AP equals to 4.5 units in its length, side BP equals to 6 units in its length. So we take the base as AP times the I to the base, that is BP, over 2. AP is 4.5, BP is 6, divided by 2. 6 over 2 is 3, and 3 times 4.5 is 13.5. So in total, we should find out that the area of the right triangle APB is equal to 13.5 square units minus the area of segment BP. We already found out that the area of segment BP is equal to 4.088 square units. And 14.5 minus 4.088 is equal to 9.412 square units. So if we found out that the area that we are looking for in this question, that is the area of this green shape, is equal to 9.412 square units. But again, the area of this green shape is equal to 9.412 square units. So we finish with the first question. In the next step, I will present you with the second question, and we'll solve the second question using two different methods. In the second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. In the drawing, we have a semicircle. AB equals to 10, that is to say the diameter of this semicircle is equal to 10 units. BP equals to 6. And AP equals to PC equals to x. Again, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So, first of all, we define the center of this semicircle. This point is point O. The diameter of this semicircle is 10, therefore the radius must be equal to 5. The radius OA is 5. The radius OB is also 5. The next step, we join points O and P together by straight line. Point O is the center of the semicircle, point P is the point on the semicircle itself, therefore OP is the radius of this semicircle, that is equal to 5 units in its length. By doing this, all those constructions, we can do the associated triangle, triangle AOP. Why triangle AOP is an associated triangle? Because side AO equals to side OP equals to 5. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in triangle AOP, there are those two equal angles. So those two angles are equal to each other. So if the size of this angle is alpha, the size of this angle must be also equal to alpha because they are equal to each other. Likewise, in the big associated triangle, triangle APC, why triangle APC is an associated? Why triangle APC is an associated triangle? Because side AP equals to side PC equals to x. So in the big associated triangle, triangle APC, in front of those two equal sides, we have those two equal angles. But this angle equals to alpha degrees in its side, therefore this angle must be also equal to alpha degrees in its side because they are equal to each other. So in the big associated triangle, triangle APC, alpha plus alpha is 2 alpha. Therefore, this third missing angle must be equal to 180 degrees minus 2 alpha. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small associated triangle, triangle AOP, alpha plus alpha is 2 alpha, and therefore this third missing angle must be equal to 180 degrees minus 2 alpha according to the same rule. So in the next step, we prove that those two associated triangles are similar to each other according to angle similarity rule. So I'll copy the big associated triangle APC and the small associated triangle AOP in a new page, and we prove that those two associated triangles are similar to each other according to angle similarity rule. What is the length of side AC of the big isosceles triangle APC? From the moment it is very easy to see that AC in total equals to 10 plus 6, that is 16. So side AC of the big isosceles triangle APC is equal to 16 units in its length. So actually, those are the two isosceles triangles. Triangle APC, the big isosceles triangle, and triangle APO is the small isosceles triangle that are copied from the original drawing. So in the next step, we prove that those two isosceles triangles are similar to each other according to angle similarity rule. So write those two isosceles triangles are similar to each other. First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So we shall prove that all the angles of the big isosceles triangle APC are correspondingly equal to all the angles of the small isosceles triangle APO. And therefore, those two isosceles triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big isosceles triangle APC is similar, this is the sign of similar, to the small isosceles triangle APO according to angle similarity rule. And for the fact that those two isosceles triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big isosceles triangle APC over side, this is side AC. The side AC of the big isosceles triangle APC over side AP of the small isosceles triangle APO is equal to side PC of the big isosceles triangle APC over side PO of the small isosceles triangle APO. Again, from the fact that those two isosceles triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AC of the big isosceles triangle triangle APC over side AP of the small associated triangle APO is equal to side PC of the big associated triangle APC over side PO of the small associated triangle APO. AC is 16 over AP is X, and it is equals to PC is also X, over PO is 5. So in total, if you found out that 16 over X equals to X over 5. Here we will cross multiply this equation and get that X squared equals to 16 times 5. So here we take root out of this equation and finally get that X equals to the square root of 16 times 5. The square root of 16 is 5, so inside the root we left the square root of 16 is 4, so inside the root we left only 5. 4 times square root of 5, in terms of numbers, it is equals to 8.94 units. So in total, if you found out that the length of this line segment AP is equals to X, it is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equals to X, it is equal to 8.94 units in its length. So finish with the first method. In the next step, I present to you how to find out the length of this line segment AP is equals to X using a second method. Okay. So in the second method, we use the rule that I've already mentioned in the first question, that the perpendicular to the base of an associated triangle bisect the base. Okay, again, we use the rule that says that the perpendicular to the base of an associated triangle bisect the base. Triangle APC is an associated triangle because side AP equals to side PC equals to X. So from point P, we go perpendicular to the base AC. Repeat again, from the vertex P, we go perpendicular on the base AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point P and the base AC. This point is point M. So according to the rule that I mentioned, the perpendicular PM bisect side AC. AC is 10 plus 6, that is 16. The base AC equals to 6 units, to 16 units in its length. So the perpendicular PM bisect the base AC. AC in total is 16. So each half must be equal to 8 units in its length. The first half AM. The first half is AM. And it is equal to 8 units in its length. And the second half is MC, that is also equal to 8 units in its length, according to the rule that I mentioned. Well, we define the center of this semicircle. This point is point O. The diameter of this semicircle is 10, because AP equals to 10, therefore the radius is 5. The radius OA is 5. The radius OB is also 5. In the next step, we join points O and P together by a straight line. Point O is the center of the semicircle, point P is the point of the semicircle itself, therefore OP is the radius of the semicircle. It equals to 5 units in its length. What is the length of the small line segment line 7 OM. From the moment it is very easy to see that OM equals to AM minus AO. Again, OM equals to AM minus AO. So I write it down. OM equals to AM minus AO. So OM equals to AM. AM is 8 minus AO. AO is 5. So in total, OM equals to 8 minus 5, this is 3. OM equals to 3 units in its length. The small line segment OM equals to 3 units in its length. So in the next step, we'll implement the Pythagoras theorem on the right small triangle POM. So copy the right small triangle POM in your page and we'll implement on it the Pythagoras theorem. Here by PT is the relation for Pythagoras theorem. The hypotenuse PO is the radius of the semicircle that is equals to 5 units in its length. PM is the missing side, and you just now found out that the side OM equals to 3 units in its length. So actually, this is the small right triangle POM that I got it from the original drawing. In this right triangle POM, the square of the hypotenuse is PO square, and it must be equal to PM square plus OM square. The hypotenuse PO equals to 5 units in its length. Therefore PO square is 5 squared, that is 25. And it is equal to PM square. PM is the missing side, so we need as it is, plus OM square. OM is 3, therefore OM square is 3 squared, that is 9. So in total we found out the 25 plus 2 PM square plus 9. Here we subtract 9 from this equation. And we get that 25 minus 9 is 16, so PM square equals to 16. Here we take root out of this equation, and finally we get that PM equals to the square root of 16, that is 4. So if you found out that the missing side PM equals to 4 units in its length. Actually, this is the missing side PM that is equal to 4 units in its length. So in the next step, we'll implement the Pythagoras theorem with the big right triangle PAM. So we call it the right triangle PM in our page. We'll implement on it the Pythagoras theorem. The hypotenuse PA equals to X, that is the line segment that we are looking for in this question. AM equals to 8 units in its length, and PM equals to 4 units in its length. Here by PT is the relation for Pythagoras theorem. So actually, this is the right big triangle PAM that I copied from the original drawing. This big right triangle PAM PA squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. So I write it down. PA squared, that is the square of the hypotenuse, is equal to PM squared plus AM squared. PA is x, therefore PA squared is x squared, and it is equals to PM squared. PM is 4, therefore PM is 4 squared, it is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, it is 64. So in total we shall find out that x squared equals to 16 plus 64. 16 plus 64 is 80. So x squared equals to 80. Here we substitute x squared by 16 times 5. Now we take a root out of this equation and find again that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. 4 times square root of 5 is 8.94 units. So actually, in both methods, we found out that the length of this line segment AP is equal to x. It is equal to either 4 point square root of 5 units in its length, or in terms of numbers, the length of line segment AP is equal to x is equal to 8.94 units. Okay, we finish with the second question. In the next step, I'm going to summarize the lecture. We start with the first question, of course. Our test in the first question is to find out the area of this gun shape. So in the drawing we have a semicircle. BC equals to 10 units in its length. That is to say, the diameter of this semicircle is equal to 10 units. In addition, we know that this is angle ABC, that is the right angle. PC equals to 8 units in its length. Again, our task is to find out the area of this gun shape. So first of all, we join points P and B together by a straight line. By joining points P and B, we get that peripheral angle BPC. Peripheral angle BPC subtends on BC, that is the diameter of the semicircle, and we know that any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. Therefore, peripheral angle BPC is equal to 90 degrees in size according to rule 5. In the next step, we implement the Pythagoras theorem on the right angle BPC. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right angle BPC, BC is the hypotenuse, so the square of the hypotenuse is BC square, and BC square equals to BP square plus PC square. Repeat again, the right angle BPC according to the Pythagoras theorem. BC squared, that is the square of the hypotenuse, equals to BP squared plus PC squared. BC is 10, therefore BC squared is 10 squared, that is 100, plus BP squared. BP is the incidence size of electricity, so it is BP squared plus PC squared. PC is 8, therefore PC squared is 8 squared, that is 64. So in total we shall find out that 100 equals to BP squared plus 64. Here we subtract this 64 from this equation, and finally found out that BP square equals to 100 minus 64 is 36. So BP square equals to 36. Here we took a root out of this equation and finally found out that BP equals to the square root of 36, that is 6. So the missing sign BP equals to 6 units in its length. In the next step, we define the center of this semicircle. This point is point O. The diameter BC equals to 10, therefore the radius must be equal to 5. So the radius OB is 5, the radius OC is 5. We join points O and P together by straight line. OP is the radius of the semicircle, that is 5, equals to 5 units in its length. And we have here uh, AC is a straight line according to what is given as the question. So if you focus on the left side of the straight line AC is point B, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have if the left side of the straight line AC is point B? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in triangle APB, the right triangle APB, we define this angle as alpha. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. According to what is given as the question, the big angle ABC is the right angle. Angle ABP equals to 90 degrees minus alpha. Therefore, this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is equal to 90 degrees. That is the size of the big angle ABC according to what is given us the question. So the missing angle here must be equal to alpha. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we prove that the right triangle ABP is similar to the right triangle BPC. We prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the angles of the right triangle APB are correspondingly equal to all the angles of the right triangle BPC, and therefore those two right triangles are similar to each other according to angle similarity rule. So okay, together we found out that the right triangle BPC is similar. This is the sign of similar to the right triangle APB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle ABP over side BC over side BC of the right triangle PBC is equal to side AP of the right triangle APB over side PB of the right triangle PBC, and it is also equal to side PB of the right triangle APB over side PC of the right triangle PBC. PB is the common side that belongs to both triangles. Now, again, we derive that AB over BC equals to AP over PB equals to PB over PC. AB is the missing side, so it is over BC. BC is 10 over AP. AP is the missing side, so it is over PB. PB is 6, and it is equals to PB is 6 over PC. PC is 8. So in total, we should find out that AB over 10 equals to AP over 6 equals to 6/8. Those two expressions are equal to each other, so we get the first equation from those two expressions is are equal to each other. So according to the first equation, AP over 6 equals to 6/8. AP over 6 equals to 6/8. Here, multiply this equation by 6 and finally found out that AP equals to 6 times 6 is 36/8. We divided both the numerator and the denominator of this number by 4. So 36 over 4 is 9 and 8 over 4 is 2. So in total AP equals to 9/2. So this is side AP, this equals to 9/2. Those two expressions are equal to each other, and therefore we get the second expression from those two expressions that are equal to each other. So to the second equation, you get that AP over 10 equals to 6/8. Again, AB over 10 equals to 6/8. Here we multiply this equation by 10 and finally found out that AB equals to 10 times 6 is 68. Here we divided both the numerator and the denominator of this number by 4. 60 over 4 is 15 and 8 over 4 is 2. So in total we should found out that AB equals to 15 halves. So actually this is side AB, that equals to 15 halves units in its length. So in the next step we defined this angle as theta and we implemented the law of cosine in triangle POB. Actually, the law of cosines is true in any triangle. So this is triangle ABC that could be any triangle. In triangle ABC, AB equals to A units in itself, AC equals to B units in itself, and BC equals to C units in itself. Angle BAC equals to theta, decreased in size. This triangle ABC, the following equation is true, that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Implement the law of cosines in this triangle BPO. According to the law of cosines, in this triangle BPO, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. But again, this triangle BPO, according to the law of cosines, cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. 5 squared is 25, so it is 25 plus 25, that is 50, minus 6 squared is 36. So in the numerator in total we have 50 minus 36, that is 14. 2 times 5 times 5 is 50. So in the denominator in total we have 50. So in total we should find out that cosine theta equals to 14 over 50. Cosine theta equals to 14 over 50. Our test is to find out the value of angle theta, the size of angle theta itself. In order to find out the size of angle theta itself, we'll operate on the result of the operation cosine on theta, on the result that is 14 over 50. We'll operate the opposite function of cosine, that is r cosine. In this way we get the value of theta itself. Like exactly like in this example, we know that the square is the inverse function of a square is the root. So if we take the number 3 and we square it, we get 9, because the square of 3 squared is 9. Now, in order to get number 3, the original number 3 itself, we will have to operate the opposite function of the square, that is the root, on the result 9. In this way we get 3. Why? Because if we do the root of 9 is 3. So in order to get the original number, we have to do on the result the inverse function of the function itself. Why? Because the inverse function cancels out the operation of the function. In this way we get the original number itself. So in order to get the value of cosine itself, you will have to do the opposite function of the cosine, that is r cosine, on the result that is 14 over 50. In this way we get angle theta itself. So the opposite function of cosine is r cosine. We will operate the opposite function r cosine on the result 15 over 50. In this way we get angle theta itself. Why? Because the inverse function cancels out the operation of the function itself. In this way we get the original number itself before the operation of the function. So arc cosine of 14 over 50 will give us angle theta itself. And arc cosine of 14 over 50 is 73.74 degrees in size. So we should find out that the size of this angle theta is equal to 73.74 degrees. In order to find out the area of the green shape, we'll have to find out the area of segment BP. What is the area of segment BP? The area of segment BP equals to the area of sector BOP minus the area of triangle BOP. See it again. The area of segment BP equals to the area of sector BOP minus the area of triangle BOP. So what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. Okay, and the area of sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. And therefore, the area of this sector BOP must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees in its size, over 360 degrees. R is the radius of the semicircle, that is 5, therefore r squared is 25. So pi r squared is 25 pi times 73.74 degrees over 360 degrees. The value of this expression in total is 16.088. So in total we should find out that the area of this sector BOP is equal to 16.088 square units in its size. That is the area of the sector BOP minus the area of this associated triangle, triangle POB. Why triangle POB is an associated triangle? Because PO equals to OB equals to 5. Okay. So we use the rule that says that the perpendicular to the base of an associated triangle bisect the base. PB is the base of the associated triangle, triangle OPB. So point O, we draw perpendicular on the base PB. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PB. This point is point M. According to the rule that I mentioned, the perpendicular OM bisects the base PB. PB is 6, therefore each half must be equal to 3. So PM is 3. PO, the hypotenuse, is 5, so in the right triangle OPM, 5 squared minus 3 squared equals to OM squared. 5 squared is 25, minus 3 squared that is 9, 25 minus 9 is 16, so OM squared equals to 16. Here we took order of this equation and we get that OM equals to the square root of 16, that is 4. OM is the height of the base PB, the area of triangle POM is equals to the base PB times the height MO over 2. PB times MO over 2. PB is 6, MO is 4 over 2. 4 over 2 is 2, and 2 times 6 is 12. So in total we should find out that the associated triangle PBO is equals to 12 square units in its size. So the area of the sector BPO minus the area of triangle BPO is 16.00 minus 12, that is 4.088 degrees in its size. So in total we should find out that the area of segment BP equals to 4.088 square units in its size. Our task is to find out the area of this green shape. The area of this green shape equals to the area of the right triangle APB minus the area of segment PB. Again, the area of this green shape equals to the area of the right triangle APB minus the area of this segment BP. The area of the green shape equals to the area of the right triangle APB minus the area of segment BP. What is the area of the right triangle APB? This is equal to the base, that is AP, times the height, that is PB over 2. AP is 4.5, PP is 6 over 2. 6 over 2 is 3, and 3 times 3 times 4.5 is 13.5. So there this right triangle APB is equals to 14.5 square units in its size. Once the segment BP, we already found out that the segment BP is equal to 4.088 square units. So 14.5 minus 4.088 is equal to the of the green shape, that is actually 9.412 square units. So in total, if you found out that the of this green shape is equal to 9.412 square units. We finish with the first question. In the next step, I presented to the second question, and we solve the second question using two different methods. In the second question, our task is to find out the length of line segment AP that is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. AB is 10, that is to say, the diameter of this semicircle is equal to 10 units in its length. BC equals to 6 units in its length. AP equals to PC equals to x. Again, our task is to find out the length of line segment AP that is equal to x. We have to find out the value of x. We define the center of this semicircle. This point is point O. The diameter AB is 10, therefore the radius is 5. OA is the radius, that is 5. OB is also the radius, that is 5. We join points O and P together. By straight line. OP is also the radius of the semicircle, that is 5. By doing all those constructions, we can deduce the associated triangle APO. Why triangle APO is an associated triangle? Because side OP equals to side OA equals to 5. And we have the rule that in front of equal sides in the triangle there are equal angles. So if you relate to the associated triangle AOP in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. Likewise, in the big associated triangle APO, one triangle APO is a triangle APC. One triangle APC is an associated triangle because side AP equals to side PC equals to x. So in front of those two equal sides, we have those two angles that must be equal to each other and their sizes. Well, the size of this angle is alpha, therefore the size of this angle must be also equal to alpha. So in the associated big triangle APC, those two angles are both equal to alpha. Alpha plus alpha is 2 alpha, therefore this perpendicular angle must be equal to 90 degrees minus 2 alpha. According to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small associated triangle POA, those two angles are equal to alpha. So alpha plus alpha is 2 alpha, therefore this perpendicular angle must be equal to 180 degrees minus 2 alpha according to the same rule. In the next step, I covered the big associated triangle APC and the small associated triangle AOP in the new page, and we proved that those two associated triangles are similar to each other according to angle similarity rule. So actually, those are the two associated triangles that are correct from the original drawing. This is the big associated triangle APC, this is the small associated triangle AOP. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So I can prove that all the figures of the big associated triangle APC are correspondingly equal to all the figures of the small associated triangle APO. Therefore, those two associated triangles are similar to each other according to angle similarity. And from the fact that those two associated triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the associated triangle APO, actually it is, this letter is C, that side AC of the big associated triangle APC over side AP of the small associated triangle APO is equal to side PC of the big associated triangle APC over side PO of the small associated triangle APO. AC is 16. You can see here that AC in total equals to 10 plus 6, that is 16, over AP. AP is X, that is the line segment that we are looking for in this question. And it is equal to PC. PC is X, according to what is given in the question, over PO. PO is the radius of the semicircle, that is 5. So in total, if you found out that 6 over X equals to X over 5. Here we cross multiply this equation, and we found out that X squared equals to 16 times 5. Here we took out of this equation, and we found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in total, if you found out that X equals to either 4 point square root of 5, 4 point square root of 5 is 8.94. So if you found out that the length of this line segment AP is equals to X, it is equals to either it is equals to 4 times square root of 5 units in its length, or in terms of numbers, AP equals to 8.94 units in its length. We finish with the first method. In the next step, I present it to you. The second method, how to find out the value of this line segment AP is equal to X according to the second method. In the second method, use the rule that we have already used in the first question, that says that the perpendicular to the base in an associated triangle bisect the base. APC is an associated triangle because AP equals to PC equals to X. So from point P, we go perpendicular to the base AC. AC is 16, because it is 10 plus 6, that is 16. So from point the vertex P, we go perpendicular on the base AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AC. This point is point M. According to the rule that I mentioned, the perpendicular PM bisects the base AC. AC is 16, therefore each half must be equal to 8. AM equals to 8 and MC equals to 8. So, adjoint points on P divided by 7, OP is the radius, that is 5. AO is also 5. So what is the length of OM? OM equals to AM minus AO. Again, OM equals to AM minus AO. So OM equals to AM, that is 8, minus AO, that is 5. So in total, OM equals to 8 minus 5, that is 3. OM equals to 3 units in its length. In the next step, we implemented the Pythagoras theorem on the small right triangle POM. So I copied the small right triangle POM in a new page, and we implemented on it the Pythagoras theorem. This is the small right triangle POM according to the Pythagoras theorem. In this small right triangle POM, PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. PM is 5, therefore PM squared is 5 squared, that is 25. And it is equals to PM squared. PM is the missing side, so if this it is, plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total, if you found out that 25 equals to PM squared plus 9, here we subtracted 9 from this equation, and finally found out that PM squared equals to 25 minus 9 is 16. PM squared equals to 16, we took out all of this equation, and finally found out that PM equals to the square root of 16, that is 4. So the missing side PM equals to 4 units in its length. In the next step, I copied the right big triangle APM in a new page, and we implemented on it the Pythagoras theorem. This is the big right triangle APM that I copied from the original domain. According to the Pythagoras theorem, PA squared equals to PM squared plus MA squared. PA is x, therefore PA squared is x squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus MA squared. MA is 8, therefore MA squared is 8 squared, that is 64. So in total, x squared equals to 16 plus 64, that is 80. So x squared equals to 80. We substitute 80 by 16 times 5, so x squared equals to 16 times 5. Here we took out of this equation and found that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So in both methods we found out actually that the length of this line segment AP is equals to x. It is equals to either 4.5 units in its length, or AP is equals to x is equal to 8.94 units in its length. Okay, thank you very much.